Hello, my name is Frits de Mul and I would like to talk about energy in the electric field. This presentation is part of a series of presentations about electromagnetism and topics. Energy in the electric field. Suppose we have an electric field available produced by a distributed charge density ρ in coulomb per cubic meter, enclosed in a volume V with surface A. The question is, how much energy did it cost to build up the electric field by positioning the charge density ρ? We will derive the following expressions for the electric field. The volume integral over the charge density times the potential with a factor 1/2. Rho is the density of free charges and V is the potential function. Or the energy is the volume integral of the electric field times the displacement. First, energy as a function of the density and the potential. Assume we have a charge Q in the origin and that produces an electric field in point P. The potential in P is Vp as a function of Q. How much energy is needed to bring another charge, this Q, from infinity to P? Here it comes. The energy will be small q times the potential present in P. Suppose we have now n charges in the origin, n charges qi. That will mean that each charge will produce its own potential in P, and the total energy to bring small q to P is given by the sum over all the potentials. Now we suppose that we have more charges, j-1 charges, qi, and the charges are not necessarily all at the origin, but they are at pi. And now we bring charge small q is qj, another charge to be placed at point P, is pj, as it is seen here. What is the energy needed for this operation? To place the first charge, there is no energy needed because there are no charges present. To place the second charge, the energy will be Q2 times the potential produced by Q1. The third charge, Q3 times the potentials produced by Q1 and Q2. And total energy needed to position all the charges with the preceding charges present is the sum over all the charges plus times the potential, the sum over all the foregoing potentials. So the total energy needed to position all the n charges qj at pj with preceding qi's present is given by this expression here, as we have seen before. And please note the summations. We can write this as 1/2 of the summations over here over all the charges. Summation is I and j both from 1 to n, and that factor 1/2 is to avoid the double counts. Note the summation limits. The summation is over all the charges, each in the field of all other charges. Here is the expression again. And suppose all charges are distributed as charge density. Here all the charges, and we now distribute them as charge densities. Then we have to sum over all the charges, each in field of all other charges. That means now divide the volume V into volume elements dV, and they will have charge rho dV. calculate the potential from all other charges at that spot, and integrate over the volume. And that will end up with 1/2 of an integral over rho times V produced by all the charges, because we have dV. This is the expression for rho dV, and if the electric material is present, V originates from all the charges, free and bound, and rho originates from the free charges. Those are the only charges that are transportable from the outside. And this means that we end up with the expression for the energy is 1/2 of the volume integral over the free charge densities times the potential, the total potential. That's the first equation we had to derive. The second one now is the energy as a function of the electric field. And now we operate in the following way. The energy to build a charge distribution is the same as the energy to destroy it. How we can do that? Well, transport all the charges to infinity and record how much energy is released. How? We place a conducting sphere with radius 0 at 0. And now we blow up until the radius reaches infinity. And during blow up, we sweep all charges to infinity. By that sweeping to infinity, suppose that we now have reached the radius r. Here we are blowing up to infinity, blowing up the sphere. The charges that are originally inside the sphere, they now lie on the surface of the sphere because they were swept while blowing up the sphere, and that those charges produce the same average E field as if they were inside. That's due to Gauss. The question is how much energy is involved in increasing the radius from r to r plus dr, and then the second question is integrate the answer from r is 0 to infinity, and then we have our answer. Here we are the two questions again. First question, how much energy is involved in increasing the radius from r to r plus dr? Consider a surface element dA. And the free charge in dA is q free, dq free is sigma free times dA. Sigma is the charge density in coulomb per square meter. What is the work to shift dA from r to r plus dr? That is, dW is the force times the way, the path. The force is dq times E, and the path is dr. Here are the two vectors, E and dF. Or, the force is sigma free times dA times E dr. And since E and dr have the same direction, we can write it as sigma free times E times dV. dA times dr is dV. So the work needed to shift dA from r to dr is given by this expression here. The question is now, what is the E and the sigma free? Because we only know the rho and the sigma free. Here is the situation. We take a Gauss pillbox. In the pillbox, the charge is sigma free dA, and that's the same as the displacements times dA. We have used Gauss law here. What electric field acts on dA? Because that electric field has to be used in displacing dA from r to r plus dr. Well, we have the total field produced by all the charges just outside the conducting sphere, and that is sigma over epsilon naught, using Gauss. The self field is the field produced by the surface layer itself, and that self field is 1/2 times sigma over epsilon naught, using the pillbox here. And thus the acting field on the charge in the pillbox, apparently due to all other charges, is the total field minus the self field is 1/2 of E naught, E total. So what is the work to replace dA from R to R plus dr was given by sigma free times the electric field here times the volume element. We use the Gauss pillbox. The acting E field is 1/2 of E total, 1/2 of E. And this means that dW is 1/2 of D times E times dA times dr. And dA and dr have the same direction. And so we can write that dW is 1/2 of dA times dV. Here is that expression again. And we can write dW is 1/2 of dA, d times A times dV. Blow up the sphere now. All charges go to infinity. We have W is 1/2 of the integral of dE, d times E times dV, as given here. Conclusions. We have derived the following expressions. The first one was the integral over the volume of the free charges, free charge density times the potential, with a factor 1/2 to avoid double counting. And B is the volume integral over the displacements times the electric field with a factor 1/2. And in fact, this is also avoiding double counting. An example. Parallel plate capacitor. That is shown here with the D field and the electric field, charge Q minus Q. The electric energy is given by the free charges times the potential, and that is the potential times the surface charges is 1/2 of V times Q free, is 1/2 of CV squared, and C is the capacitance. The second one is the integral over the displacements times the electric field. We use Gauss is D times sig, D and sigma are equal, E is V over D, and C is Q over V, and then we end up with 1/2 of, this is the D, this is the E, so we can write for the dV is A times D, when we perform the integration over the volume, AD, surface times this distance between the plate, and then we can write it in this form. Q sigma times A is the Q, and here we have the potential, so that's also 1/2 of the capacitance times the potential squared. And this is the end of the presentation. Thank you very much.